This video is a computer project that creates an LED binary clock using a Raspberry Pi computer. Once you've passed the preliminary Pi tutorials, it's time to do something a little more meaningful, something that expands your programming skills and understanding of electronic hardware. Analog round-face clocks have been around for years with 2 or 3 hands. With the computer era, digital clocks are introduced with 4 decimal digits. This video introduces a binary clock with 6 binary LEDs. Since we're limited to 6 LEDs, the minutes will be displayed in solid lights and the hours in flashing lights. Other than the Pi computer with a monitor, keyboard, mouse, power supply, you will also need the listed hardware components. A small breadboard, one being used is 3 inches by 2 inches, 6 LEDs, light emitting diodes, either white or blue, 7 jumper cables, each with a male end and a female end, 6 330 ohm resistors, and an internet connection to obtain the time. The circuit for each light starts with a pin on the Pi connector, then a resistor, then a LED, and return to a common ground pin. The only wiring concern is the longer leg of the LED must be connected to the resistor. LEDs only light if current is passing through them in the appropriate direction. If you connect the shorter end to the resistor, the LED will not light. We use resistors to limit the voltage across our LEDs, so one is added in series for each of the lights. Failure to use the resistors will result in shortened useful life of your LEDs. The resistors come with bands on the outside showing their value. For the 4-band coding variety, the first band is the tens digit of the resistance value. The second band is the units digit of the resistance value. The third band is a tens multiplier. And the last band for critical applications is the tolerance range the resistor meets. Some resistors are not exactly as labeled. The tolerance band shows the variance. Since we use 330 ohm resistors, we will be looking for one of the with bands orange, orange, brown for 30 plus 3 times 10. The tolerance band is not critical for this application. A resistor in the range 300 to 500 ohms should work. The breadboard has subsurface connections. The upper 2 and the lower 2 rows on the breadboard are subsurface connected inside the breadboard. For example, all the lower holes are connected by the blue horizontal line. The vertical rows in the 2 center groups of 5 holes are also subsurface connected, as shown by the 2 vertical blue lines. Anything connected to a subsurface connected group of holes is electrically connected to each other. The red lines show the subsurface connection of the circuit for the rightmost light. It starts with the black computer jumper that connects the upper right corner. Then the red line shows the subsurface connection to the resistor. The resistor carries the current over the center of the breadboard. The subsurface connection carries the current to the LED, and the LED carries the current to the outer row of holes. The horizontal red line shows a subsurface connection to the black ground jumper leading back to the computer. All the LEDs will be sharing this one jumper. It's time to wire your breadboard. Do not add the black computer jumper cables for now, but arrange your resistors as shown on the board. Add the LEDs with the longer end of each connecting to the resistor. The computer has a 26-pin connector. An explanatory graphic is shown beside it. We're only going to be using 7 of the pins in the right column. These pins are general purpose input-output GPIO connections. Each of the pins is assigned a name in the green box beside it that will be used in our program. The top green 1 pin is GPIO pin 14, GPIO 14. This graphic is shown rotated to make it easier to read the labels. It will be shown full screen at the end of the video. Start wiring the jumper cable female end to the 4th pin across the top row. It should be easier to connect all the jumpers in order 1, 2, 4, ground, 8, 16, 32 to the computer pins before plugging any to the breadboard. Now plug the male jumper end to the breadboard so they are on the same column with the resistor. Start with the rightmost 1 LED that connects to pin 14, the 4th pin. Then pin 15, then 18, then ground, then 23, 24, 25. This is the same order as on the computer pins. With the wiring complete, we need a program to light the LEDs. Python compiler comes with the Pi computer software. It is a compiler, which means that when it starts, it first checks for any errors in the program, then, if none, proceeds executing one statement at a time. If any errors are noted, the program will have to be updated before the execution phase may begin. With the breadboard complete, let's discuss some programming issues. Python is sensitive to the case of each variable. They must be entered in the same case. Capital C, small e, small l is not the same as capital C, capital E, capital L, capital L. We will be using 2 system subroutines to drive the GPIO output pins and determine the time delays. We will also be using variable arrays, for, and while Python statements. It's always a good habit to document your code. Python allows inserted comments that begin with a pound sign. Anything to the right of the pound sign is ignored by the Python compiler on the remainder of that line. Comments add clarity and are very helpful when you revisit your program. Assumptions you make today may be forgotten tomorrow. In the example, we documented that day equals 1 is assumed to be Monday. While most computer variables contain one value, an array variable may contain a group of values surrounded by square brackets. In our program, all the GPIO lead names are placed in one variable that then we'll use a for statement to apply to all of them. The first value in an array variable is called the array variable square bracket 0 square bracket. Then array variable square bracket 1 square bracket. The Python for statement allows for one or more indented statements to be executed for each value in an array variable. In the above example, the numbers 1, 2, 3, 4, 5 would appear on the output device. In our program, each of the LED pins is going to be initialized to an off state and identified to the computer as a GPIO output lead. The Python while statement allows one or more of the following indented statements to be executed as long as a condition is true. This allows us to create the clock sequence by coding while true. All the indented statements following will be repeated again and again. To interrupt the program, hold down the control button and press the C key. The true condition could be replaced with some other logic expression that could change, but for our situation it will be constant. Older languages have a number of jump, go-to statements which allow the execution to jump to other programming statements. It's more appropriate to use while and similar logical loops to make your program easier to understand as it executes in a progressive manner. This is called structured programming. Python does not support go-to jump statements. This is the first screen of 5 of our program. A full screen version of the program will be shown at the end of the video, so you may pause those frames and more easily read the code. Notice the liberal use of comments. If you've not downloaded GPIO subroutines before, you will need to use the apt-get command to load them before running the program. We named this program binaryclock.py, and once you've coded it and named it the same way, it can be executed using the same command. Use of the GPIO subroutines requires the sudo root command be used. Since we're using 2 system subroutine packages, we will need to identify those to the Python compiler. System routines allow use of complicated system functions instead of having to code them yourself. User-written subroutines will be explained in the next video, Roman numeral clock. Import rpi.gpio as GPIO loads the GPIO subroutines. From time import sleep loads, we'll be able to use the sleep command to delay program execution for a set number of seconds. GPIO cleanup initializes the general purpose input-output system pins. GPIO.setMode parent GPIO, BCM parent identifies that we'll be naming the GPIO pins in this program by their BCM names. There are other Pi pin naming conventions, but we'll be using this one. The next section of the program defines the LED pin name for each binary digit. The one LED is pin 14 and the others follow. Remember, the ground pin is between 4 and the 8 pins on the computer. I listed it in the same order here. There's no programming for the ground pin, it's only listed for completeness. All the pins are included in the array variable LED pins. Notice the use of the square brackets around the pin names. The for loop then executes the setup and the output statements for each pin name. The setup command identifies this pin will be used for output. The output statement then turns the light off. The HMS variables contain the hour, minute, and second from the Internet time routines. They are printed on the screen to aid debugging the program. If they appear on the screen or advancing, we know they're being collected from Internet and the program is running. Any problems will be in the remainder of the code. This program uses the AND Boolean operator, ampersand. The minute and hour are represented in the computer as binary numbers. For example, the number 29 is represented as 011101. The minute logic ANDs the minute number with the number representing each bit. If that bit is on, it results in a non-zero value and the GPIO command turns the LED on, true. Since we have 6 LEDs, the minutes are displayed in solid lights and the hour in flashing lights. The minutes will be displayed for 2 seconds, then the hour will be flashed on for 5/100ths of a second, and 1/10 of a second off 5 times. Any of those values may be modified. Since the while condition is always true, the loop only stops if interrupted manually. The hour is converted from the internet 24-hour clock time to AM/PM hours. The hour logic results in the same manner as the minutes, however uses 2 for statements. One controls how many times the hour LEDs flash. The HR bits array contains values for each of the bits. The second for statement cycles through each bit. If ANDing it with the hour value results in a non-zero value, that LED is turned on. The code is much more compact, but more difficult to follow. You can enter your program in Python, save and execute it. From the command screen, enter sudo idle. Code your program and then click on File and Save As in the Home Pi directory and assign the name Binary Clock. Python saves its files with a .py suffix file type. Then exit the Python shell IDLE program. Enter command mode. Type the matching letters case will be critical. Type ls, the list command, to confirm you're in the right directory by displaying all the files. Binary clock py name should be one of those displayed. Since we're using the system GPIO routines, your program must be executed in system mode, so we'll proceed the Python command with sudo. To execute your program, type sudo python binaryclock.py. The program will loop until interrupted by holding down the control key and pressing the C key. The traffic light signal lights video is already available and uses the same wiring board, but we changed the 6 LEDs to traffic light colors. Another planned project in this series is a Roman numeral clock. Roman numeral clock is another example of practicality but a fun programming project. Hope to have it posted in the near future. Hope you enjoy these projects and expand your pie cooking abilities. If you have any comments, please email us at elpmetvideos@gmail.com. ASL interpretation was provided by my daughter, Mary Schmidt.